In this lecture, we've traced the magnetic force from its relativistic roots. We began by analyzing the force between current-carrying wires using only electric fields and the geometry of length contraction. From this line of reasoning, the magnetic field emerged not only as a fundamental ingredient, but as a convenient mathematical construct, a way to summarize how electric fields behave in moving frames. So this might lead you to believe that the magnetic field is not real, in the same sense that the electric field is real. However, such a conclusion is a little too hasty.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Lesson 112, the magnetic force equation. So last time we talked about the relativistic origins of magnetism, and we're going to basically continue that discussion, but I wanted to open by addressing something, a small mistake from the last lecture. We didn't use the results. I didn't catch the mistake. We did it correctly for the case of the parallel wires where you had parallel currents, but there was a slight mistake in the anti-parallel current case for the charge density, and I want to correct that now. So let me remind you of the configuration. Let's call this the source wire. Okay, and so we're going to imagine that there is a positive current, I sub s, which of course means that there is a drift velocity for the electrons going in the opposite direction. And then we'll have our test wire, which will have an opposite current, which of course means that the drift velocity of the electrons in that wire is opposite that of the drift velocity of the electrons in the source wire. So here is where the mistake came in. When accounting for the, remember we always use this relationship, right, that the lab frame, I'll even label it lab, positive charge density, that's the stationary ions in the wire, positive charge density in the lab frame is equal to the negative charge density in the lab frame, because it's electrically neutral in the lab frame. But the problem is that in the lab frame, the negative linear charge density, the electrons are already moving, so they are already Lorentz contracted. So the negative charge density in the lab frame, because those charges are moving with respect to the lab frame, this is actually a Lorentz contraction with the drift velocity of the electrons times the charge density in the rest frame. When we write that the charge density in the test frame, the test charge frame, that's the test wire for the negative charges, is equal to gamma 2 times the drift velocity, because essentially the drift velocity is slow, so the relativistic addition of velocities is negligible, and you can really treat it kind of like a Galilean transform. So just because they're going the opposite direction that you're going, and you're both moving at the same speed, but in opposite directions, you see it passing you with twice the velocity. This wouldn't work if the drift velocity got very large and close to the speed of light. Then it would break down. You'd need to use the actual velocity you get from the addition of velocities formula from relativity. And so last time we had said that this was just equal to the lab frame charge density. And that's where we made our mistake. What we needed to do was, just like we did in the other case, the parallel case, to divide this by gamma sub v sub d. So this is the missing piece that we had. And then when we put it all back together and utilized the equivalence of the charge densities in the lab frame, we would write that lambda prime net, the net charge, would be equal to lambda minus times gamma 2 v sub d over gamma v sub d minus gamma v sub d. So we were missing this term here. And I want to show now that you get the same result with the opposite charge that we did for the parallel wire case, because that wasn't clear, and if you had worked with the formula I gave you, you'd have noticed that there was a discrepancy in the magnetic force for parallel currents versus anti-parallel currents, when in fact they are equal but opposite in sign. Okay, so let me show you that. We'll use some binomial approximations, one in particular. So if we expand what these gamma factors are, right, let me write that over here. So 1 over the square root of 1 minus v squared, where, remember, c, we're allowing that to be equal to 1, so our velocity v is always less than 1. If we do a binomial expansion on this, if we do the binomial expansion in the denominator, we would get 1 over 1 minus 1/2 v squared. But you can rewrite that, I'll just leave it up here, I guess, as 1 minus 1/2 v squared to the minus 1, which means we can again do another binomial approximation on that, and we'll get 1 plus 1/2 v squared. Whereas just the square root of 1 minus v squared we would approximate as 1 minus 1/2 v squared. So if we do that, first thing I want to do actually is factor out this gamma here, gamma v sub d. And so that will give me gamma of v sub d times lambda minus, that's going to leave a gamma 2 v sub d here. This will then become gamma squared v sub d minus 1. And if I apply these binomial approximations to this term here, gamma v sub d lambda minus, and in here I will get 1 plus 2 v sub d squared times 1 minus v sub d squared minus 1. After simplification, this will give me that lambda net prime is equal to gamma v sub d lambda minus times v sub d squared minus 2 times v sub d to the 4th power. Now to first order, this is exactly the same, except that now we're using the negative charge density, so this has a negative sign built into it. But they're both, to first order, proportional to v sub d squared. And so they're equal and opposite in sign. Now these higher order terms, let me just make a comment on that. So technically, like the Coulomb's law that you're familiar with, and certainly the magnetic force equation that we're going to derive today, are first order approximations to these force laws. There are actually higher order relativistic corrections that need to be made to them. And so when I say that these two are equal to first order, that is consistent with the usual classical laws that we deal with. The higher order terms are real, and they are a consequence of relativity. So we don't worry about the higher order terms necessarily here, because these speeds are really low. The drift velocity, remember, is very slow. It's just the extreme number of electrons, right, in a unit length of wire that gives rise to such a strong and noticeable effect in the macroscopic scale. The only thing, the only difference is to first order would have been lambda plus, so gamma lambda plus times the drift velocity squared for the parallel current configuration. I know the last lecture may seem very difficult to understand. The basic idea, though, is actually pretty simple. In the moving reference frame of your test charge or your test current, or whatever you want to call it, you are seeing an increased charge density, or at least a distortion in the charge density, that gives rise to an electric field in that frame. And that electric field in that moving frame, back in the lab frame, manifests itself as a magnetic field. And it's these very strange directional properties of this force that we're going to kind of address today to try to get the, come up with a form for the magnetic force equation that we would expect, basing it on a relativistic origin like we did last time. And so that's what we're going to try to do. But again, if there's a relative velocity between two things, you will see a Lorentz contraction. And if you've got a train rolling by and it's got charges on it, then you're going to see, because of the Lorentz contraction, an increased charge density. Now in the case of current carrying wires, it gets a little complicated because it's not, you've got the stationary positive charges from the lab frame that are appearing to move to the left. That's where a lot of that's coming from. In the case of parallel currents, right, the conduction electrons in the source wire are actually moving alongside you, right? But their charge density is not what you would have expected. It's not what it was in the lab frame, because in the lab frame they were moving. So you have to kind of do this Lorentz contraction from the rest frame to get what they are in the lab frame. And so once you're back moving alongside them, now you're in their rest frame, and so they have a different charge density than what you had assumed from the lab frame, you see? So it gets a little bit complicated, but the basic idea is that when there's relative motion between two frames of reference, you'll see length contraction. And so that will cause the charge density to distort in some way, either increasing or decreasing. I guess it would always be increasing, and that will give rise to an electric force. That force will exist in the direction that connects you. And that is what gives rise to this seeming magnetic force, which is always perpendicular to the motion of the test charge back in the lab frame. So we're going to isolate several properties that we'll use to basically construct an equation, a force equation, for this magnetic force. And so the first property, call it property 1, is that this magnetic force is proportional to the test charge and the sign of the charges and the magnitude of the charges in the source frame as well. So the source of the magnetic force, that's the moving charges, and the test charges, both of these contribute to the magnetic force. So from last time, we found that in the moving reference frame, we had a force which had this gamma, q sub t, that was the test charge, lambda plus, this would be for the parallel configuration, right, where you see a net positive charge in the source wire. V sub d squared divided by 2 pi epsilon naught times r, where r was the distance between the two wires. Okay? And that's because this was the electric field from a long straight wire. We derived that in an earlier lecture, which I'll put right here as reference. And so we see in this equation for the force, which if we're in the, and we also showed that in the lab frame, this manifests itself as q sub t lambda plus v sub d squared over 2 pi epsilon naught r, also without the gamma term, right? So it says that the lab frame force, which will be magnetic in nature, is, to get it in the moving frame, we just apply the Lorentz transformation. But as you can see, the test charge appears directly in the force equation. So that takes care of this part. What about the source charge? Well, that actually appears inside of here, in lambda, the charge density. So that's property 1, both the source charge and the test charge. It gets complicated though, right? Because in the case of the parallel wires, the source charge is actually a positive charge. Yes, even though it's the electrons that are moving that's causing it. All right, property 2. The magnetic force has a bilinear dependence on the test charge velocity and the source charge velocity. This was not so apparent to us last time because we assumed that the test charge, the magnitude of its velocity was the same as the source charge's velocity. We said they're both moving at the drift velocity. And that's fine for, currents, because that's just what conduction electrons do. But we can imagine that our test charge was not the current in a wire, but maybe just a stream of electrons out of an electron gun or something like that, whose velocity we can control based on how much energy we give them, right? So I want to try to disentangle the v sub d squared term and make an argument to show to you that it would actually, if we let those velocities be different, that it would be bilinearly proportional to both of these. And so we'll start with, for the parallel wire case, lambda net. Actually, I'm not going to write it with gamma. I'm going to just take it to an earlier version where we had lambda plus, which we'll just call lambda in this case. We're not worried about that too much, times gamma. First time I'm going to write, I'm going to say that this is the test charge velocity, because this is the stationary ions, or the stationary positive charges. And since we're the one that's moving, and we're moving at the speed v sub t, in our frame of reference, they appear to be moving in the opposite direction at that same speed, because they were stationary in the lab frame. So that's this term here, whereas the electrons will be moving at their speed. That could be different, right, than what ours was, because they were already moving, right? So we're going to go ahead and give them this speed here. And using the same binomial approximations that I showed you just a moment ago for the antiparallel current case, we can write lambda times 1/2 v sub t, v sub t squared plus v sub s squared. So just simply using the binomial approximation like we did before, here and here, it will simplify to an expression that looks like this. Notice I didn't factor out a factor of gamma. Now what I want to do is I want to basically parameterize the test charge's velocity. I want to say that the test charge velocity is equal to some factor alpha times v sub s. Right? So if it's going faster than the drift velocity of the source electrons, then this would be, alpha would be bigger than 1. If it's going slower, it would be smaller than 1. Basically, alpha is the ratio of the test charge velocity to the source charge velocity. So that I can rewrite lambda net prime, lambda over 2 V sub t squared would be alpha squared, v sub s squared plus v sub s squared. You can see I can factor out v sub s out of both of these. Give me lambda over 2, v sub s squared times alpha squared plus 1. But if I multiply this equation on both sides by v sub s, this becomes v sub s times v sub t is equal to alpha times v sub s squared, which means that v sub s squared can be written as v sub s times v sub t divided by alpha. So that would look like lambda over 2 times v sub s times v sub t. I'd probably want to put alpha squared plus 1 divided by, I'm going to put the 2 here with the alpha, over 2 alpha. So you can see now that if alpha is 1, that means both v sub s and v sub t are equal to each other. Then you're going to get 1 squared plus 1 is 2, divided by 2 times 1 is 1. And so we get that it's just v sub s times v sub t, or v sub d squared, right? So that's the case where this was v sub d squared in the way that we formulated it in the last lecture, okay? But here I've kind of pulled them out so you can see how it changes when they're not the same. And you see that, in fact, since the force, magnetic force, was proportional to the net charge density in the moving frame, then you see that it has this proportionality to both the v sub s and v sub t. So that's our second property. Let me just write it here. Property 2, F mag is proportional to v sub t and v, that's not a dot product by the way, that's just v sub t times v sub s. So it's the speed of the source charges that are generating this magnetic force and the speed of the test charge, right? If the test charge is 0, there's no magnetic force. Similarly, if the source charges are moving 0 velocity, no magnetic force. Okay, property 3. Magnetic force in general is proportional to 1 over r squared. So I know you're saying, well, we got that it was proportional to 1 over r, the separation distance between the wires. And that's because that was a very specific geometry. Remember that the electric force for a long straight wire is proportional to 1 over r, not 1 over r squared. And that's a consequence of that very specific geometry. So we're going to consider the case where they're no longer wires, but just single point charges moving through space. Let's think about what that would look like. Imagine that the charge that's moving, say the source charge, is some kind of sphere. So in the rest frame of that moving charge, it would be perfectly spherical, yes? Yeah. And so in the lab frame, if you see that charge going by, what you're calling the lab frame charge density, or linear charge density, will be proportional to, we'll have to do a Lorentz contraction in the direction of the motion, right, or the direction of the relative velocity as it zips by. So to us, this sphere actually looks kind of like this. It looks a little more oblate, yes? Yeah. Now imagine that we have this test charge, right, that is going to maybe travel right alongside it. If it's traveling right alongside it, so its velocity is the same in the same direction. In the primed system, this guy looks like a sphere again, yes? Because there is no Lorentz contraction. There's no relative velocity between them, yes? As they're moving along? Yeah. But it's in this frame, right, that we would be calculating what the repulsion between them should be. So in the prime system, because the charge density is less, the repulsion is not as much. You see? Yeah. There'll still be an electrical force which pushes them apart along in the direction of the line that connects them. But it's not as much as you would get if you were in, say, the lab frame where you see a higher charge density. And so the charge is compressed in the direction of velocity, right? So this is traveling this way, right? So called v sub s. But when we travel alongside it, it looks like a sphere again. Yeah. And so it has a lower charge density. So what happens is that the way that we account for it in the lab frame is we say, okay, well, we have the electric repulsion due to the charges that are there. But because there's a magnetic force, it's actually a magnetic attraction. I'm going to put a problem in the homework where you actually calculate this. And there's an attractive force that reduces that repulsion. And so from the lab frame, it's explained by the presence of an electric force and a magnetic force that's counteracting the repulsive force of the electric charge. In the moving frame, however, there is no magnetic force because there's no relative velocity between you and the source charge, so there's no magnetic field. But there is a larger charge, or there's a smaller charge density, so the electric repulsion is not as much. But what does the electric field look like, say, in this system? It's pretty clear, since these are just the forces between test charges, which we're saying are spherical in shape, right? That the Coulomb's law tells us that in the prime system, that the force is proportional to 1 over r squared.
Yeah.
And we know that when we transform back into the lab frame, right, that these are related, right, by a factor of gamma, in fact. So that this 1 over r squared dependence will follow us back to the lab frame just for point charges, just like the 1 over r dependence followed us back to the lab frame for the long straight wires. We had 1 over r because it was a long straight wire, and the electric field from a long straight wire goes like 1 over r. For point charges, they go like 1 over r squared. And so that will follow us back to the lab frame. So our magnetic force will have a 1 over r squared dependence in general. That could change for various geometries, but for point charges anyways, it'll be 1 over r squared. All right, property 4. This one is not so easy to write. Property 4. So I'll just say directionality, angular dependence, and the magnetic field. So here I'm actually going to introduce the magnetic field, but not yet. The first thing we need to understand is the contribution to the magnetic force from the motion of the source and the displacement vector that connects the source to the test point. So I want you to imagine a source with its velocity v sub s, and let me pick a test point right here, and this will be our test charge. It will have a velocity as well, which we'll call v sub t, and then I'm going to draw the line that connects them. This is the displacement vector, and I'm going to counter that with a case where we still have v sub s, but this time we have a displacement vector like this, v sub t. When do we see a Lorentz contraction? Right? So we see a Lorentz contraction, right, when we take when the relative velocity, there are two components to the relative velocity, relative to this displacement vector r, and there is a parallel component. That means that the relative velocity is along the displacement vector that connects the 2 points. So that's in this direction. And you can get that by simply taking the dot product of the relative velocity with the displacement vector. That's projecting the relative velocity onto the displacement vector. That'll give you the component that is in that direction. But there's also a perpendicular component. It is the perpendicular component in which we see a Lorentz contraction. So if we imagine moving this test point from this configuration here, where the perpendicular component of the relative velocity is 0, there is no contraction. Versus here, where perpendicular component of the relative velocity is maximized, we have Lorentz contraction. In fact, we have maximized Lorentz contraction. And if it's anything in between, then it'll be something in between here and here. And I think I can draw this in a way that will make it look more meaningful. So when there is no contraction, again, going back to this model of our charge as being spherical in shape, that's when there's no contraction. And I'll draw an in-between where we have some contraction. And I'll put our test particle over here. So still have v sub s this way, v sub t this way, and the displacement vector is along here. And then here, where we have maximal contraction. So here it's very oblate, you see? So here, when we maximize the relative velocity that's perpendicular to the displacement vector, we get the maximum Lorentz contraction. Here, it's minimized. There's no Lorentz contraction. And otherwise, it's basically related to the sine of the angle between them. So it seems that this quantity, the magnitude of the source velocity times the magnitude of the displacement vector, right, times the sine of the angle between them is somehow important. But this, right, is just V sub s cross r hat. Let me just say that the magnetic field is going to be proportional to V sub s cross r hat. So you can see that under certain conditions we get no Lorentz contraction and therefore no magnetic field. And in some situations we do get Lorentz contraction and magnetic field. But it's a little bit like angular momentum, right? Where everything is taking place in a plane. You've got stuff spinning in a plane, but the angular momentum is always a vector that's perpendicular to that plane. So this magnetic field is actually going to be perpendicular to the plane that connects these two. So if this is all in the xy plane, let's say, the magnetic field is going to be in the z direction, out of the page or into the page, depending, okay? So that takes care of the contribution from just the source and the displacement vector. But it also depends on the velocity of the test charge, right? Because we assume that it was always aligned in a specific way here, always in the same direction as the source charge motion, right? That way we could kind of disconnect it from the source charge contribution to this magnetic force. But because the relative velocity doesn't just depend on the source charge, it didn't depend on the test charge velocity here because I kept it always the same. I just made it the same as the source charge direction, right? But if we allow it to change now and we allow it to vary, then what happens is the component of the relative velocity that's perpendicular to the displacement vector right now depends on the test charge velocity if I allow that to change. Okay, and so that's going to manifest itself in a different way. The easiest way to see it, and here we're going to say that F mag is proportional to, remember these are vector quantities. I haven't been very careful in writing these out as vectors, but what we're talking about here, they're always vectors. So from what we talked about before, the Lorentz contraction affects only the dimensions of an object that are parallel to its direction of motion relative to an observer. The dimensions perpendicular to the motion remain unchanged. But we observed, right, that this magnetic force was always perpendicular to the motion of the test charge. It was never in the same direction as the test charge was moving. Therefore, it's a force that does no work, right? It cannot change the kinetic energy of the test charge. Once we accept that the magnetic force must be a vector built from the velocity vector of the test charge, the velocity vector of the source charge, and the displacement vector that connects those two, and that it must be linear in the velocities and perpendicular to the test charge velocity's direction, then we are almost forced into this triple cross product formulation for this functional dependence of the magnetic force. It's the simplest and most natural expression that is consistent with all of the physical observations. This part here is going to end up being proportional to B. So we're going to think of this as like the B field. So this will actually define a direction that's both perpendicular to both the displacement vector and perpendicular to the source velocity direction. You can draw pictures of this, but it's very hard to draw in 3 dimensions. It's much easier to work with something like this in real space. So let me set this up for you, what we should be thinking of here. So I've got, and I can rotate it around a little bit to see, we'll call this this is going to be a right-handed coordinate system. So if I call this the positive z direction, that means that when I curl the x-axis into the y-axis, that my thumb should point in the direction of the positive z-axis. So this will be positive x, this will be positive y, negative y, this will be positive z, and then back behind here where I don't have an axis labeled will be negative z, z, x, and y. For what we're going to consider here, we're always going to have our source charge moving in the plus z direction. So I put a little piece of tape here on the z-axis to remind us that the source charge that we're talking about in this case will be located at the origin, and it's traveling in the plus z direction, so it's going this way. And I'm going to put our test charge here in the xz plane at y, but y is equal to 0, right here at this point. So this is where our test charge is. Now, the first part that we did here, right, the vs cross r, right, what is that? Well, that's the vector that results from that is this vector here that I have, I guess it's a brown color, and we're going to call that our B field. So I'm going to assume a positive charge carrier here. I'm going to assume a negative test charge here. And this is the direction of our B field. And it's proportional to Vs cross R. And so the full magnetic force, the direction of the force, is going to depend on this triple cross product. the second part, the Vs cross r, I'm just going to think of as this B. It's always going to be in this direction. Wherever I move this test charge, as long as it's in the xz plane, that's the direction that B is. Now I can specify what the test charge velocity is. So if we wanted to do something like what we did with the parallel wires, right? Remember where we got an attractive force, that would have been where we had a positive source charge current and then a negative test charge current. So I'll make this yellow vector be the velocity vector of the test charge. And so if I have it going in this direction, since it's negative charge, we're going to use a left-hand rule. If it was a positively charged test charge, we'd use a right-hand rule. So that can be a little bit confusing, but how does that work? Since I said that the test charge is negative, I'm going to use this left-hand rule. So what I do is I take the velocity vector and I use my hand to curl it into the direction of the B field, which is down, right? So when I do that, trying to squeeze it in like this, right? My thumb is pointing in the direction of the force, okay? So the force is always perpendicular to the velocity, but also perpendicular to this B field direction down here, okay? Since the velocity vector is in the z direction, the B field is in the minus y direction here. That means that the force is in the negative I direction by the left-hand rule, because I curl it in. So we can explore different configurations, right, for this. And you can even think about, well, when do we see, a Lorentz contraction? So here's our source charge moving like this, right? What if our velocity vector was in this direction, just like this? So we're headed straight for it, right? Well, if we curl it using the left-hand rule, our thumb is pointing in the minus z direction. B field's in the minus y direction. Our velocity is in the negative I direction. I'm using the I, J, K, and I'm sometimes mixing them up. Sometimes I'm saying X, Y, Z, and sometimes I'm using the unit vector directions I, J, and K. I hope that's not confusing. Remember, we use I for X, Y, J for Y, and K for Z. So I think I'll just stick to X, Y, Z. But in the homework and stuff, I'm probably going to use I, J, and K. So if our velocity vector is in the minus X direction, which it is, because this is the positive X direction, and the B field is, as always in this case, going to be in the minus Y direction, then the force from the left-hand rule is going to be in the minus Z direction. Okay? But why is there a force at all? I mean, you're thinking, what exactly is going on? I'm headed straight for this guy, right? You might think there's no force. Well, there is. If you imagine yourself in this test frame, what do you see? You see the source charge moving to the left and coming at you, right? So it's the part that's moving to the left that you're going to see a Lorentz transformation from. One of the homework assignments that I have is I ask you to explore these two situations. When is the relative velocity component that's perpendicular to the displacement vector 0, or when is there no Lorentz contraction? And there are two cases where that can happen. So there would be no Lorentz contraction if I move this reference point here onto the axis of the velocity of the source, right? This is the plus z axis. And the reason why is because now the displacement would be entirely in the direction of the source velocity. And so there would be no magnetic field. This term would give us 0, okay? So there would be no magnetic force. But anyway, that'll be in the homework. So you can play with this and look at various, we can even go out of the plane. So we can say, okay, what's the magnetic force, say, when I'm headed straight up? I'm headed in the plus y direction. Well, now the angle, right, between them, you don't even know how to apply the left-hand rule, right? So if it's headed straight up, how do I apply the left-hand rule? There's no way I can bend it any way that I want, right? I could bend it this way, I could bend it this way. It's kind of like all those directions, they cancel out and the force is 0. Another way to look at it is the sine of the angle between them. What's the sine of 180 degrees? That's the angle between them. 180 degrees is the same as the sine of 0 degrees. And what's the sine of 0 degrees? 0. So the force is 0, right? So let's do this. Let's have it swivel around. So here, when the velocity is headed straight for the z-axis, so in the minus I direction, the minus x direction, and we apply the left-hand rule, right, we see the force is in the minus z direction. So as I rotate this around, what happens? You can kind of see. You can just move your hand and your thumb. Now the force is towards the wire. All right, if we go out this way, it's going to head out in the opposite direction. Yes? But you'll notice it's always the same magnitude, right? It's always the maximum, right? Because the sine of the angle between them is always 90 degrees, so it's 1, right? Now what if I make it in this plane? So as down here, Right, the angle between us is 90 degrees, so the force is maximized. The left-hand rule tells me it's in the minus z direction. As I rotate the velocity vector up this way, the angle between the B field and the velocity vector is increasing. Right, it's headed towards 180, or I could go down this way, maybe it'd be easier. It's going to decreasing from 90 and headed towards 0, right? And so you see that the force component, which is still in the same direction, its magnitude is decreasing until they're aligned, and now it's 0. So anytime you're moving in the direction of the B field, the force is 0. Now I only consider this one plane because there is this spherical symmetry, right? If I picked another point, I could just simply rotate my coordinate system and say, well, just make for ease, we'll make it here. So if I had it up here, I could just rotate the whole coordinate system until it was in that plane again, and the arguments would be the same. So there is this rotational symmetry about this. And so if we were to look at the B field at various points, what would it look like? So if I took this test charge, actually I'll take the whole, and I move it out of this XZ plane, you see what the B field is doing, right? It's changing its direction, yes? And so as a consequence of this, if we were to think about our old friend, hope I don't get poked in the eye. Well, I do have glasses, so that's probably good. Let me move this out of the way now. If I were to go back and think about our old situation where we had the wires, right? Now I'm going to let the wire, I'm going to run it into the board, right? So the wire, the source wire is coming through like this. You'll notice that this B field, right, basically rotates around in concentric circles. So you're going to get a clockwise motion. Concentric circles all the way around. So the funny thing about these magnetic field lines is that unlike the electric field lines, they don't start on charges and end on charges, right? Remember, they start on positive charges and they terminate on negative charges. These field lines don't start or end anywhere. So if I were to have a test charge move on a circular path around this wire, it would feel no magnetic force at all. Because you can't have a force in the direction of motion, you see? Okay. And so I'm going to write this property as this. Property 4 F mag is proportional to V sub t cross V sub s cross r hat. And so that triple product basically encodes all of these bizarre directional and angular dependencies that we see from the magnetic force as we've kind of shown it from a relativistic point of view. But, you know, regarding under which configurations do we see a Lorentz contraction and when do we not, right? And then there's really only one more property that needs to be listed. And I'm just going to write it over here. Property 5. F mag reverses direction for opposite charges. And that's kind of evident from this, right? You can see how if you change the sign of the charge, you can change the direction of the force. Yes? So it's really kind of an extension of property 1. And so if we throw all these together, what do they tell us, right? They tell us that the magnetic force equation is going to be something like this. Q1, Q2. Let me stick with my terminology. Q sub t, Q sub s, that's for test and source, over r squared times V sub t cross, parentheses, V sub s cross r hat. And to make it exact and not just proportional, we'll have to put in some constants. The constants is just there so that the units come out right. And for SI anyways, the SI system, it'll be mu naught over 4 pi. I think that's something like equal to 10 to the minus 7, but not worried about the constant, okay? Because that doesn't give us the conceptual insight. That's just something to make units come out right. And we can take this further and compare the Lorentz equation that we had last time, right, by noting that the magnetic field B, we'll have this part here, we'll have the source charge part into it, we'll have the radial dependence, the S cross R. And these again are vectors. So we put everything that has to do with the source charge into the magnetic field part of it, and then we can write that the Lorentz force is equal to Q sub t times E plus V sub t cross B. where the Q, so the E part, this would be if there's an electrostatic field of some kind, right? So we've been considering the case where this is 0. So it's just the QT times this. And so you put these together with this, and you get this, the magnetic force equation. These properties up here all come from these various circumstances in which you would see a Lorentz contraction, and therefore a distorted charge density. So in the frame of the moving test charge, it would appear as an electric field. But this would appear funny from the point of view of the lab frame, because in the lab frame, you would not, of course, detect that charge distortion. But that is basically, let me say, we want to have some final thoughts on this, though. In this lecture, we've traced the magnetic force from its relativistic roots. We began by analyzing the force between current-carrying wires using only electric fields and the geometry of length contraction. From this line of reasoning, the magnetic field emerged not only as a fundamental ingredient, but as a convenient mathematical construct, a way to summarize how electric fields behave in moving frames. So this might lead you to believe that the magnetic field is not real, in the same sense that the electric field is real. However, such a conclusion is a little too hasty. So while relativity shows us that the electric and magnetic fields are different manifestations of a unified electromagnetic interaction, the magnetic field B is nonetheless locally measurable via the Lorentz force on a moving charge. It's observer independent in its own frame. It's capable of energy storage and momentum transfer. And within quantum theory, it's capable of inducing measurable phase shifts, like the Aronoff-Bohm effect. So thus, even if B arises from motion and relativity, it acquires physical status in its own right, like angular momentum and temperature. So this brings us to one of the kind of great open questions in theoretical physics, which is, could there exist magnetic charges? That is, could you have magnetic monopoles that act as sources or sinks of the magnetic field, just as electric charges generate electric fields? So far, no magnetic monopoles have been discovered, but there are plenty of reasons in theoretical physics to believe that they might exist. So our exploration in this lecture is complete, but the conceptual journey is not. So we began with wires and relativity. We ended with a field that bends space, resists change, stores energy, and might yet hide deep secrets of the cosmos. Here's a quote by Werner Heisenberg that's, I think, relevant. Not only is the universe stranger than we think, it is stranger than we can think. So with that, there's the conclusion of this lecture. I hope it was helpful. I think the framework, right, will help you remember this formula. Typically, this is accessed through experimental considerations, and we'll talk about those experiments, the Biot-Savart experiment and the Ampere's experiment in the next lecture. Okay, that's it.